I will say that I kind of was able to get involved in this project through working with this food web model and talking with some folks down here and realizing that I think there's some cool implications for applying this model to the T3 experiment. So hence the Alaska connection, but I think there are some neat overlaps there in using this model. So I want to go ahead and acknowledge that this is a team effort with support from Ryan Belmore, who is with the U.S. Forest Service, Joe Benjamin, who's with USGS, and then Teddy, Kyle, and Warren have also been involved in this project. I also have to thank Warren for all of the pictures. All right, so we're going to be looking at specifically focusing in on the riparian treatments from the T3 experiment. So I think you've gotten tastes of this background on this project, and certainly we'll talk more about that today. But the idea is that there are 5 different potential treatments that will be implemented in the riparian area, and the idea is to look at kind of these different responses across the treatments. So this has some, obviously, like the treatments are in the riparian areas, but being adjacent to the stream, there's some clear connections with what's happening in these stream systems. I think Kyle did a great job of giving you that overview. And so one of the things with these type of experiments is that you can do monitoring in the stream, but it's pretty time intensive. It's and can be challenging to detect results. Beyond which, if you're looking over a longer term, it's just not feasible to be able to go out to all these streams for 50 years and say, okay, how long are we seeing these different responses? So that's where the kind of modeling approach enters in. So I will say too, I'll use these images as we go forward to talk about the different treatments, but we have 5 different ones. We've got our no action, a kind of fixed width standard OESF 30-meter buffer. We have a alder rotation that occurs underneath a heavily thinned conifer area, variable buffer widths, which depend on kind of the site conditions. And then the 5th treatment is a active habitat restoration, where there's a gap created along the stream, and some of that wood that was removed to create the gap is actually added to the stream. So we'll come back to these different treatments. But let's talk a little bit more about the stream food web model. So specifically what we're working with is called the Aquatic Trophic Productivity Model, and it was developed by Ryan Belmore and others. And this model, the ATP model, is a stream food web model that links what's happening in the stream food web to the surrounding environmental conditions. So if we think about the T3 experiment and these different riparian treatments, they have ways that they can directly impact the stream. It might be that more the canopy is opened up and you change the amount of light that's entering the stream, affecting primary productivity. You may have differences in the organic matter that's entering the stream. So there's a lot of linkages between what's happening in these stream food webs and these different riparian treatments. So in approaching this, taking this modeling approach, we had 2 specific objectives. The first was to establish hypothetical in-stream and riparian responses to the T3 treatments, and we used those to parameterize our ATP model. And then we wanted to model stream food web response to different riparian treatments in both the short term, thinking of a couple years, and the long term, looking out to say 50 years after these different treatments are implemented. So what is the ATP model? It is a food web simulation model wherein fish production is tied to the flow of energy or organic matter through the food web. So this model explicitly links these food webs to things that are happening in the physical habitat of the stream, riparian conditions, as well as terrestrial and marine-derived organic matter subsidies. And then the model simulates how the biomass of these aquatic organisms in our stream food web change through time. So clear as mud. Let's talk about what the model structure looks like. So again, I mentioned the simplified stream food web. And so we have 4 main food web members or stalks in our model. At the bottom, we have our periphyton and our terrestrial detritus. things like leaf litter that entered the stream. And then we have aquatic invertebrates that are consuming this periphyton and our detritus stalks. And then the aquatic invertebrates are themselves consumed by fish. We're predominantly focused on kind of these juvenile fish in the system, but as Kyle mentioned, it's kind of these looking at groups of different communities of fish in these systems. And then we also have arrows that go the opposite direction that indicate that fish and our aquatic invertebrates can have top-down control on the other food web members. So all together, what we see is that, there we go, these 4 stalks make up our simplified river food web, and that all of the dynamics, both these consumer resource-driven interactions determine how this system operates. I should use the clicker and not try and do it on the computer. All right, so to this simplified food web, we've connected some of these other inputs. So we've added sunlight and nutrients, so things that affect primary productivity in the stream. We've linked in some of the riparian conditions, so these riparian vegetation contribute leaf litter to the stream. They also affect the amount of light that is reaching the stream. And they're also a source of terrestrial invertebrates, which can link into fish consuming said invertebrates. And the strength of all of these interactions are mediated by the physical conditions of the site. So, for example, we can take water temperature. And water temperature influences the bioenergetics of all of our stream organisms, our fish, our invertebrates, as well as the growth of our periphyton and the decay of organic matter. Similarly, we can say things like channel hydraulics affect the model in multiple places. So we have things like, for instance, water depth. And the depth of the water contributes to light attenuation and how much light is actually reaching the stream bed to fuel primary production. So this is the structure of the model that we're working with. And into that, we put a number of site-specific inputs. So here, before I start, I just have to say thank you to all of you who have been collecting this data, both for the T3 sites, but then through other projects. It meant that when we went to parameterize this model, there was a great wealth of data available to be able to plug in some of these things. So the inputs under riparian conditions, we have things like the vegetation cover of the stream, the composition, kind of what portion are deciduous versus conifers. We have stream shading. We also have a number of parameters related to water quality, stream temperature, nutrients such as nitrogen and phosphorus, turbidity, and things like stream discharge. And then for habitat, we're looking at channel width and depth, the gradient of the stream, substrate size distribution, and channel retention. So using this group of environmental inputs, we were able to parameterize the model for a generalized T3 site. And I emphasize the generalized piece because by using a generalized rather than a single specific site, what we can do is run the model for a number of each of our different riparian treatments and compare that response at a single site. So essentially, we're removing a level of variation in looking at these responses by using this generalized version. So once we have all of this data together, what we can do is run the model. And what does that look like? So to start, here's an example looking at our fish biomass. Here I've zoomed in so that you can see the seasonal variation within a single year of the model run. So we have time in the x-axis, and then our y-axis is an estimate of daily fish biomass per square meter. And what we can see is that we do have some seasonal variation in what's happening in that fish population. I do want to say that as this process is ongoing, it's iterative, where we receive feedback and kind of continue to modify our model, I would say focus on the trends of these lines rather than the exact numbers of our fish biomass. But can we capture what's happening in terms of pattern and look at differences relative to one another? All right, so we looked at fish, but we can also look at all of our other food web members. So we can look at our aquatic invertebrates, both our community of grazers as well as our shredder collector invertebrates. We can look at what's happening in the seasonal dynamics of our periphyton community, as well as our deciduous detritus broken up detritus broken up both into deciduous and conifer sources. So in this case, I'm using the data that's being shown here is from a single model run with a single set of parameters. But one of the things we know about the ATP model is that it's sensitive to site conditions. So to look at kind of how this baseline biomass level, how these baseline biomass levels may change as we look at individual sites, we can add some site variation into our model run. So here what I'm looking at, this is, again, our fish biomass within a single year where I have varied the environmental conditions to represent the range of what we might see in our different T3 sites. So that's highlighting some of the data that you saw in that variation that Kyle and Warren showed you. And what we see is that in red, we have this average value, and then the blue bars or bands are a confidence interval around that average value. So what we can see is that there's variation among our sites, and we know that. And that's consistent with what we're seeing in the monitoring data. But essentially, moving forward, what we're going to be doing is focusing more on kind of this average value and relative differences across our treatments rather than this variation between sites. All right, so another way to look at this data is to look over a longer scale. So now I still have time on my x-axis, but I'm running the model out for a whole 50 years. And here I've got time 0 that's marked by this horizontal line, and that's the time at which these treatments are implemented. So the time to the left of that vertical bar is essentially our pre-treatment conditions. So right now, I haven't changed any of these inputs in response to treatments. We have a straight line going all the way across. And what this is doing is it's plotting average annual fish biomass. So because there's no change between our before and after treatment implementation, essentially what this is representing is our no treatment condition, that we don't expect there to be any differences between our pre-treatment implementation and our post-treatment implementation as a result of that treatment. All right, so now that you've seen a little bit about what the model looks like and how it runs the sites, let's talk about how we approach these different treatments. So a big part of this was we had a workshop last fall where we pulled together people who are familiar with the T3 sites and familiar with the area and then the type of different treatments that were being implemented. And we asked people how they thought that environmental conditions would change in response to each of these treatments. And we asked them to actually draw out these response trajectories. So in some cases, that was pen and paper, marks on a whiteboard. In other cases, we have this interface page to our model where you can go in under user controls and select different variables and actually draw out how you would expect things to change. So for example, if you thought that there was going to be an increase in stream temperature in response to one of your treatments, you might draw a line with an upward trajectory. But that was only part of the question, because then there's this aspect of duration. How long do we think that increase in temperature is going to be sustained? So for example, if we look at it from, like say a change in stream shading, if during one of the treatments you remove some trees that creates an opening in the canopy, you might see a decrease in stream shading that's sustained for a few years, but then over time as other vegetation grows up, and you have canopy closure, that stream shading might gradually increase again to where you were before. So again, this really kind of this part of the modeling exercise relies on this local knowledge and expertise about what's happening in the systems, and then kind of the available data that we have for these T3 sites. So at the end of this exercise, we had a series of response trajectories. And basically, we determined that there was about 12 different parameters that we were looking at that we think would change in response to these treatments. And then for each of those parameters and each of those treatments, we had a list of how they change, these different drawn-out trajectories. So let's jump in ahead and look at different treatment responses. We'll touch more on what these look like, but just to say, again, let's look at these curves relative to one another. So we have our active habitat restoration, our fixed buffer width, our no action, our variable buffer, and our alder rotation treatments. And what we can see is that they differ relative to one another, both in terms of the duration that these changes are present for, and the type of reaction. So just to zoom in, here we have our fixed buffer width. So again, this is a standard 30-meter buffer. And what we're here showing is that we have a single line drawn, but because there were some different ideas about how these responses would occur, there's some variation on that line. You know, if scenario A happened, it might do this. If scenario B, it might do that. So what we see for our fixed width buffer is that generally we have a kind of return to background conditions in about 15 to 20 years. Our response to the next treatment, our variable width buffer, is pretty similar. That these buffers vary a little bit in thickness based on site conditions, but the group thought that the response would be pretty similar among these treatments, where we see, again, that return to baseline levels after about 15 to 20 years. When we look at alder rotation, again, this is heavily thinning and then leaving the alders, and then after about 30 years, go in and harvest those alders. So there's a second, essentially, disturbance to this model after about 30 years, which is one of the reasons why, for this particular treatment, we see a sustained response that lasts longer compared to our previous ones. And then finally, we can look at our active habitat restoration. So here, what we see is that we're creating a gap in the stream and changing the light, and that response over time gradually decreases as you look at things like the retention or how much wood is in the system and light access. So to bring it back together, we can look at what these treatments look like relative to one another. And one of the things we see is that there are differences across our treatments, both in our near term, that short couple-year window, and then in the longer term, when we look out, say, 50 years. So basically, this ATP model is a tool that can be used to generate hypotheses about how these sites will respond to the treatments. And this has implications for how you might choose to apply these treatments going forward. So I want to end by just saying thank you again to all of you who have been collecting data in this and answering my many questions about, well, what about this? Or how much variation did you see in this? So with that, just want to acknowledge the different people involved, and then I think if we have time for a quick question.